Hello everyone, I'm Paul and today we're solving problem 3405. Count the number of arrays with k-matching adjacent elements. This is hard and this one is a math problem. So here we'll go through the required concepts to solve this. We're given three integers, n, m, and k. And we need to return the number of good arrays that we can form with these integers. Now, a good array has a size n. Each element in the array is in the range in between 1 and m, and k is for the pairs in which the current element equals the adjacent previous element in this array. So this is how we can find a good array, and we need to return the total number of good arrays that we can form with this. And we need to return this modulo 10 to the power of 9 plus 7. Let's say n is 3, m is 2, and k is 1. Here we have 4 good arrays. For example, let's take the first one. Here we have one valid pair, and k is 1, so this is okay. If we take this value, the adjacent previous value is the same, so k is okay. Next, every value goes from 1 up to 2 as a maximum, and m is 2, so this is also okay. And every array has a size of 3, so this is also okay. So this is a good array, and these are also good arrays. And these are the only 4 good arrays that we can build with these conditions. So the result in this case is 4. Now, in case you didn't notice, this is a combinatorics problem. So now let's see how this works and how can we use this to solve this problem. Let's say we have 5 spaces and we can only fill one of these spaces, and we need to know how many ways do we have to fill one space in these 5 spaces. So we can fill this one, or we can fill this one, we can fill this one, we can also fill this one, or we can fill this one. So the result of 1 in 5 is 5, and we can write this as NCR, which in this case is 5C1. So 5C1 equals to 5. And in case you know, there's a formula that we can use to get this. NCR equals n factorial divided by r factorial times n minus r factorial. So in this case, we have 5 factorial divided by 1 factorial times 5 minus 1 factorial. And this is 120 divided by 24, and this is 5. So this 5 is this 5. That's the first thing you need to have in mind. Now let's say we are trying to find 1 in 5, and at the same time we are trying to find 2 in 5. So we are trying to find 5C1, and at the same time we are trying to find 5C2. This means how many combinations do we have here in which we have 2 of these elements and 1 of this element. And whenever we are doing simultaneous tasks in combinations, we can multiply this to get the final result. So it's important to remember this. Whenever we are doing multiple tasks, we multiply the tasks to get the final result. Now going back to a problem, let's say n is 5, m is 3, k is 2. If n is 5, we will have arrays of size 5. And now let's go with the k part. First, we need to get the number of pairs, the number of possible pairs here. Remember that a valid pair has equal adjacent elements. So this could be a valid pair. This could also be a valid pair. This could be a valid pair, and this could be a valid pair. So here we have 4 possible pairs. And similarly, if the size of the array is 3, here we will have 1 possible pair and another possible pair. So here we will have 2 pairs. So we see a pattern here. The number of possible pairs is n minus 1. In this case, n is 5, so the possible pairs are 4. And now we know k is 2. So we can find 2 valid pairs in these 4 pairs. So remember, we can do 4c2. And this is how I think about this visually. We know we have 4 possible pairs here, and we are trying to find every combination of 2. So this and this could be one valid combination. This and this could be another valid combination. Now we have 2. And this could be another valid combination. Now we have 3. This and this is another one. Now we have 4. This and this is another one. So now we have 5. And finally, this and this is another valid combination. So here we have 6. And 4c2 is 6. Now we know m is 3. So if we were doing all of this with, let's say, a number 1, for example, well, let's say we are at the first combination, we'll have a 1 here, a 1 here, and a 1 here. This is a valid pair, this is another valid pair. We know k is 2, so this is a valid combination. But we also need to do the same with every other number from 1 up to m. So let's say we are again at the first combination, we have this and this, but now here we have a 2, 2, and 2. So we also need to count this, and we also need to count the same for when we have 3, 3, and 3. And this keeps going up to m. In this case, m is 3. So for example, we need to do this combination with 1, 1, 1, 1, and we also need to do this with 2, 2, 2, 2, and so on. So I think now you get the idea. And what this means is we need to multiply this with m. So here we do 6 times 3, this is 18. Now we are counting all the pairs here, and we need to add every other element. So let's say we have this valid pair and this valid pair, and we have this element here. If we are using a 1, for example, for the elements in this pair, here we need to use a 2 or a 3. And if we are using a 2 for these elements, here we need to use a 1 or a 3. And if here we are using a 3, here we need to use a 1 or a 2. So for each empty cell, now we have m minus 1 possibilities, meaning 2 possibilities in this case. And how many empty elements do we have up to this point? Well, we have the amount of pairs minus k. So we can do 2 to the power of 2 in this case. And finally, remember, this is a new task, and we need to add this task here. And the way to add tasks is through multiplication. So 18 times 4 is 72. So this is the final result, and just to be clear, we will use this formula. This is for the first part, and this is for the second part. For the first part, we do n minus 1 ck times m, and for the second part, we do n minus 1 because we are subtracting the m that we are using here, m minus 1 to the power of n minus k minus 1. Remember, here we are subtracting the pairs that we used here. Time complexity for this will be roughly big O of n, and this could be more inefficient because we will not pre-compute this. If you pre-compute this part, this could be overall more efficient. And space complexity will be big O of 1. So now let's go with the code and hopefully you will get the idea. Here we won't pre-compute anything, so we literally need 2 lines of code. This will be enough. So first, the mod value will be 10 to the power of 9 plus 7. And then we return the combination. In Python we can use this function, so we call comb with n-1 k. This is the same as saying n-1 ck, and we need to do this times m, and we need to add one task here. Remember, we use multiplication to add another task, and here we will use the power function in Python, and this is m-1 and n minus k minus 1, and we need to mod this by the required value. So this is it for the code. Now let's submit this and see if it works. And as you can see, this works. This is efficient, and this can be more efficient if we pre-compute the combination part. Remember that. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.